Okay, so so basically, if you want to deep learning, you need enough computation. So a GPU is kind of necessary. The good thing is there are actually reasonably affordable GPUs out there. For instance, the K750 from NVIDIA is, GTX 750 costs around $100, $150, and you will probably need a reasonable power supply, but again, the GTX 750 will probably work with your current power supply. If you don't have that, find somebody else who has, or if you're really desperate, talk to Barnabash and me and maybe we can help you, but overall, you will need computation. Without that, you can't do it. The second thing is, you should not implement everything from scratch, because it will take you too long. Okay? So use existing toolkits, and I'll get to which toolkits a little bit towards the end of it. There's probably about 4 or 5 good toolkits out there. If you don't use any of those, it could be problematic. As in, again, it might take you longer than this semester to actually get something meaningful done. Okay, good. Again, please ask questions anywhere throughout, because this class is clear for you guys, so don't be shy. And the other thing is, I'll be around after class, and basically ask me as much as you want then. Just figured it's easier to do it right after class. If there are too many people, we'll go up to my office and then we talk there. Okay. So what we'll be trying to cover in the next 3 lectures is essentially 3 parts. So first I'll go over basics. And with basics, I mean things like the perceptron. We'll actually look at stochastic gradient descent and probably the convergence rule for the perceptron. The reason why this is useful is because this is about as simple a proof as you can get for stochastic gradient descent algorithms. And this is probably as deep as we will go into proving things there. There are some proofs on the slides, but I'll probably skip that. The second thing is because it serves as a very nice point of departure to either go towards kernels, which we'll do much later, or towards deep networks. And essentially, it's different generalizations from the perceptron that will lead to one or the other. The second part then is we'll cover different parts of deep networks. So we'll look at layers, types of invariances. So actually, we'll be probably covering a little bit of group theory. Don't worry, it's just 2 slides, but it's a very convenient way of actually thinking about those invariances and then, deriving new types of layers from it. And then we'll get to something that is essentially right now one of the most exciting parts of it, namely different types of objective functions, how you can actually solve a large range of problems by essentially engineering objectives. And last, we'll talk a bit more about optimization, capacity control there, and then a lot of hidden state models. The latter will really depend on how much time we'll have left, and for the rest I'll give you pointers. And the good news is that a lot of deep networks papers are technically not amazingly challenging to read. That's usually a sign of a field at the moment making very large conceptual progress, but they are fairly creative in terms of the ideas that are in there. So read them, and then maybe you can do some nice theoretical analysis for it, which then might be a lot deeper and a lot less easy to read. And in the end, I'll cover some toolkits. Okay. So the perceptron. These are Rosenblatt and Widom. I don't know whether they showed up at work this way, but that's how they built it. No, we're not going to cover how the brain was supposed to work about 150 years ago, but we'll start actually with a little bit of biological motivation, because that's effectively where the entire name neural comes from, except that by now neural and deep is a catch-all for anything nonlinear and non-convex. They've done a very good branding. So the basic idea is that good behavior should be rewarded and bad behavior should be punished, or at least not rewarded. And you can do that and or for instance, if you kill a saber-toothed tiger, it's good for you because you survive. The more practical example where this happened was Pavlov's salivating dog. So does everybody know what happened in this experiment? Basically, Pavlov had a dog, and he would feed him, and before he would feed him, he would ring a bell. And so the dog learned to associate bell ringing with feeding. So it's not a causal connection, but it's a correlation. And the dog learned that, and so he started salivating even when he just rang the bell. Okay. So you can code this in several mechanisms. One is basically in an evolutionary framework where you basically adjust the genes, and that takes usually quite a long time unless you're a bacterium. Or by behavioral modification and learning, which is basically what I'm trying to do with you guys. I'm trying to teach you new stuff such that you then will become a more fit machine learner for your PhD. This is the last biology slide, I promise. So this is a picture of a neuron. And essentially what you have is you have like a cell body that combines all the signals. You can think of this like a CPU. Dendrites is essentially the input bus where the data comes in. And then you have synapses. This is basically the interface between different neurons where one neuron sends data out and the other one comes in. And this is essentially where you then can adjust weights. And then there's an axon, which is essentially like a long cable. So for instance, in your spine, that axon might go from your brain up to somewhere where I then move my arm or my leg, right? So this can be a couple of feet long. So now let's make a crass oversimplification. So this is a neuron in the mathematical sense. We have some inputs, x1 through xn, and we have synaptic weights, w1 through wn, and then we get an output. And in the most primitive case, I might have a linear output. In other words, what I simply have is that f of x is just the sum over wi times xi. Okay. Now, that's possibly not quite so exciting because in this case, if I then combine various neurons, well, what would I get as the final output if I did this? What type of functions can I get if I combine several linear functions? A linear function, correct. So I think we would all argue that we are more than linear creatures. And so one way of getting this nonlinearity is by just putting a nonlinearity after each of those linear combinations, and then you basically cascade them, right? So this actually works surprisingly well, and a lot of separating hyperplanes, like into spam, ham, novelty, typical, click, no click, work this way. So for instance, if you look at your ads, or let's say you do a Google search, and then you see some sponsored search keywords and so on, most of this is probably driven by something that is not much fancier than a very, very high-dimensional linear model. So with very high-dimensional, I mean something like 10 to the 10, 10 to the 11 dimensions. So this is a serious object, but it's essentially a linear model in that space. Now, one of the goals there is then to learn and estimate a separating hyperplane or learn a linear function. So we basically need to estimate the parameters w and b. So if you do this, let's say here we have ham and spam, then I might infer that any of those hyperplanes will actually do a pretty good job. Quick question, so this is a little bit of a look ahead towards something that we'll cover later. There's a couple of hyperplanes there. Who thinks the red hyperplane is a particularly good one? Who thinks the magenta one is good? Who thinks the green one is good? Who thinks the black one is good? Okay, that doesn't add up to the full audience, but I think the majority said it's the green one. Why did you think so?
Biggest area on either side.
Exactly, because it has essentially a large margin of separation. And later on, we will see how to actually find such large margin separators. So it'll turn out that this is actually the solution of a reasonably straightforward convex optimization problem. But for now, we will content ourselves with just finding any such separator. And you can immediately see that if the data were much closer together, there would be fewer such separators. And the problem would become a little bit harder. And this is exactly what it'll turn out to be the case, that the difficulty of finding such a separator will depend very much on how close the points are together relative to how widely spread out the points are entirely. So we'll put that in math. You can see an obvious problem in this. If I had even just, let's say, a single point here, right? Then the single point here would, and maybe something there, then obviously you could not find a linear separator anymore, right? Now, a lot of the analysis that I'll show you first for the perceptron is something that only works if you can linearly separate the data. This is an important issue because if you ignore this, you get a huge commercial flop. Does anybody know this game? Okay, yeah, okay, you're probably too young for that. There's a game called Black and White. Peter Molyneux was the developer lead in that. And they had this very nice idea that, okay, you play God, so those are nice games, right? And you have an avatar, in this case, I think it's this furry creature there, probably some wolf or whatever. And this avatar would learn to behave in the way you behave. So if you were a benevolent God, then your avatar would be benevolent. And if you were evil and intimidated all your followers to pray to you, then it would learn to be evil too, right? And you could essentially play and win the game either way. Now, the way how this avatar learned how to be benevolent or evil was by observing you and then basically building a linear classifier. And this works very well if you're very consistently benevolent or evil. But if you occasionally change your mind, then the avatar would get horribly confused and it would start becoming very unstable and basically the algorithm would not converge and various other things. So the bottom line being that the avatar in practice in the game turned out to be extremely hard to control. And that was the main reason why the game flopped. So morale of this story, if you have non-separable data, you should not use a perceptron in anger because it will not work. Some things that you can do in this case is, for instance, weight decay. In other words, you slightly will shrink the parameters that I'll show you in a moment, or you try to be robust towards the data, or basically you need to make some concessions to the fact that your data is not perfectly linearly separable. Okay, so this is just a bit of a warning because this cost them probably $20-30 million. The fact that they didn't use regularization. Okay, so it's expensive. So here's the very simple algorithm. This is state-of-the-art 1960s. It goes as follows. Start with a parameter w that's 0. Start with a coefficient b that is 0. And then just keep on going through the data until, you don't make any more errors. And making an error means that w.xi plus b times yi is less than 0. Okay. So let me quickly explain why that corresponds to an error. Okay. Must be a screen. Okay. Okay, so we have w.x plus b, right? And what we want is that this is greater than 0 for y being 1 and less than 0 for y being minus 1, right? So if this is greater than 0 for y being 1, then I can equivalently also transform that into y times w dot x plus b. Right? Because multiplying this entire equation with 1 doesn't change anything. If I have w dot x plus, okay, so let me do this here. W dot x plus b less than 0 for y equals minus 1, well, it's quite easy. I can just multiply it with y and flip that sign, and lo and behold, those two conditions are actually the same. So therefore, this is the only thing I really need to check. Okay. This will become a little bit more handy later on when we do SVMs. But for here, let's just assume, okay, if this condition is violated, then update W by adding a little bit of the observation to it. So basically, I'm just remembering the instance that I got wrong times the sign of the label. And likewise, well, if I, let's say, classified something as spam that I shouldn't have, then I'll just, change my threshold B, right? And likewise, B goes into B plus yi. Note there's no learning rate, nothing there. It's a very, very primitive algorithm. And I just keep on going until everything's classified correctly. Okay. Quick question. Why do I not care about the scale of W and B in this case? Why would this algorithm run identically if I multiplied everything by 5? Yes?
You're only looking at the directions.
I'm only looking at the sign, right? And so therefore, if I was to multiply W and B by any number, any positive number, mind you, this condition would still hold. Likewise, that condition would still hold. So that's why I don't care about the scale. So in that sense, the perceptron is quite an anomaly because it doesn't care about it. Now, a couple of useful things in there. Nothing happens whenever I get things right. Secondly, the weight vector is a linear combination. And so then the classifier in the end is a linear combination of these inner products. So those terms xi dot x. So when we go towards kernels, what will happen is that we will replace this by a kernel function. So if you were to replace xi dot x with a kernel function throughout, you would get the kernel perceptron. And that's essentially fast forwarding about 30 to 40 years of research. Right?
Wait, sir, what is x versus xi?
Oh, okay, sorry. Thanks for asking. So x is, for instance, a new spam or ham email. Right? xi is an old email. And so now what I do is I simply take the inner product between those two texts. I could do that simply by taking the bag of words representation for one email with a bag of words representation for the other email. Right? So if you look at what happens for the naive Bayes classifier for text, you will actually get the same type of representation. So depending on which model you use for P of xi, so P of x given ham or spam, you will get exactly the same equation. Okay. Now, this is an algorithm about as primitive as you could want it, and the question is, does it do anything useful? And there's this very, very nice convergence theorem, and it basically says, if there exists a solution, W star, B star, and that's the catch, if there exists such a solution. With unit length and this condition that, W dot xi plus B times yi is greater or equal than rho, then the perceptron converges to a linear separator, not necessarily the same, but one of them, in b squared plus 1, r squared plus 1 over rho squared iterations. Okay, so let's decode this a little bit. So first of all, what we already saw is that since we are scale invariant, whether we have W and B or 5 times W and 5 times B doesn't really matter. So the unit length is a non-issue for us insofar as, well, we can always normalize W and B to unit length, right? So that's easy. The other thing that we are requiring is that the data is contained in some ball of radius r. Well, again, that's straightforward because, well, we only have a finite number of observations, so we can always find a ball around them. And now this rho is exactly that margin of separation, right? Basically, what I showed you before in the picture, how hard or how easy it would be to actually separate one half of the data from the other. Okay. And the good news is that the algorithm converges in that number of updates. Note that it doesn't say it converges after seeing that many observations. It's only after seeing that many updates. Can somebody tell me why this could be potentially a huge difference? Okay. Imagine you're taking a class that's ridiculously easy, right? Then you're going to spend a lot of time in that class not really learning anything, right? Because you can already predict very well what the next step is. So what that means is that you will actually spend a lot of instances, in this case xi, yi, where you already know the answer and your model doesn't change, you don't learn anything. Now imagine you take a class that's insanely hard. You're updating your model at each and every step and you're going to learn a lot faster. Okay. So my goal here, and Banabash's goal, is to make this class as hard as we can while you still learn stuff. Because if we make it really easy, then you're not going to learn anything and you would have a much better time hanging out in a bar or a coffee shop, right? Or getting back to your research. Okay. So this is the Perceptron answer to the difficulty of classes. Couple of things. This result. Okay, so let me first finish answering this question. So basically, if I make very few mistakes, then I will have to do a lot of updates and basically look at a lot of data until I actually have a solution that fully separates everything. And that's basically why ideally you want to make all the mistakes right in the beginning. Question? Yes?
I might be just reading this wrong, but seems like if you shrink all the data towards the origin,
okay,
you would decrease the number of steps needed because you would decrease the ideal bias and PR.
But then the rho also decreases.
Yeah, but rho decreases. I mean, there's two factors in the top
right.
that are both squared, but there's only one rho squared in the bottom, so it seems like.
Okay. Okay. So the b squared plus 1. Let's forget the bias for the moment. So basically, that means we can. Okay, and effectively, first of all, what you can do is you can just incorporate this bias directly into W by just augmenting your parameters by 1, right? So what I'm doing is I can rewrite this as W, V in a product with X, 1, right? So if I do this, then this gives me the same expression as that. And if you look hard, you see that the norm of this object is exactly, since we assume that this is of length 1 and this is b, right, that this is basically 1 plus b squared. And yeah, okay, this has length really, r squared plus 1. Right. This is basically where those two terms come from. So essentially what you're latching onto is that I just use this representation here. So if you because if you were to rescale x, then without really taking into account that there's also a constant offset, then you could slightly misread what the theorem states. So the pure version without the bias is basically the one where you would just have r squared over rho squared. Right? So that's why that couldn't happen. Now, what really happens is if you shrink the ball of the data, right? Then also, of course, rho gets smaller, right? Because your margin of separation therefore gets smaller. And in this case, the ratio between r and rho still stays the same, so you don't win anything. What you're talking about, however, is if I, for instance, were to rescale the x's and not rescale the rest, is you're actually distorting the space, effectively. And that can actually change things quite a bit. Let me give you an example. Let's say here's some data. Nicely separable. Okay. And now what I do is I go and squish everything in one direction and not in the other. So then, the radius will, so basically what I'll get is, stuff that looks like so. And now this, of course, is a lot harder to separate. So in that sense, your intuition and your question is right. Well, if I was to rescale the data, could I make the problem a little bit harder or easier? Indeed. But once you, properly incorporate x and the constant offset with each other, this artifact goes away. So what this means in practice is that if you're actually trying to solve a machine learning problem, you should make sure that your data is properly rescaled. So in other words, if you, for instance, had something where you wanted to correlate body height and wavelength, the body height is in meters and the wavelength is in nanometers, then it's a really good idea to rescale them to maybe zero mean and unit variance, because otherwise your algorithm will have a very hard time relating 10 to the minus 9 meters to meters, right? Now, this is a no-brainer in this case, because who would do something as crazy as that? But if somebody gives you data and doesn't tell you very much about the attributes, a lot of people would actually end up doing such crazy things by mistake. So make sure you don't. Okay.
When you give the intuition WB and W1, omega B and omega 1, so when you do the omega B, why is it bounded by B squared plus 1 instead of B squared plus R squared?
Well, okay, so B squared, okay, so this is the length of my omega really. So let me call this omega tilde, if you will. And we can call this thing here x tilde. So in order to rescale everything, I would have to basically rescale W and B, that pair, if this is a W tilde, by 1 over square root 1 plus B squared. Right? So then we are in the unrescaled version of that theorem. So maybe going through the proof might actually help a little bit. Who wants to see the proof? Okay, that's less than half the audience. Okay, what should I do? Okay, let's
show a sketch. So it's between.
So that means nobody can follow the proof. Yeah. Okay, what we'll do is I'll show you this proof and we'll skip over the more general stochastic gradient descent proof. How about that? And then you can read that one up in Nesterov and Viol. Because it's actually a very neat trick and it's a template for an algorithm that we'll see a lot. So let's say we start from W and B equals 0. And what we do in the first step is we bound the increase in alignment that we get between my wi bi, which is my current estimate at time I of the W and B pair, and W star and B star, which is basically the large margin separating pair. Okay. Now, whenever no mistake happens, nothing really happens, so we only really need to stratify by mistakes. And so what we get is that W dot B inner product with W star and B star. So we just have the update rule, right? So we have Wj Bj plus Yi times Xi and 1. Because we just made a mistake, so this is our update. Remember, what happens is W goes into W plus Y times X, and B goes into B plus Y. Okay, the inner product with W star and B star. So that's just the old inner product. And then I can pull out the change. Now for the change, we know that it can be linearly separated, right? This is our working assumption. And we know that this can be linearly separated by a margin of at least rho. So it's basically the old inner product plus rho. So therefore, the alignment, in a way, between W and B and W star and B star has to increase at least linearly with the number of mistakes that I make. Note, I'm not saying anything about the length of those two vectors. We'll do that next. But I'm just talking about the absolute value, about the value of the inner product between those two. Okay? Now, the next thing that I have to do is I have to bound the length increase. Okay? So the length increase goes as follows. We basically have, again, W and B. I'm just now using Cauchy-Schwarz, right? And so this gives me that the inner product has to be upper bounded by the length of W and B times square root 1 plus B star squared, right? Yes?
So we're assuming that the optimal W is going to be unit length?
It's going to be what?
Unit length?
Yeah, that was basically the condition of the theorem, right? So the condition of the theorem was that W star has length 1. And the slight ugliness here is that I need to deal with B star. Okay, so this is just Cauchy-Schwarz. So what we now have is, as said, we have a lower bound on that inner product, and we have an upper bound on that inner product. Now, in order to make those two things actually, bite each other, we need to get an upper bound on the second term. So the first one we've upper bounded by essentially a constant. It doesn't depend on how the algorithm runs. Okay. Now for this part here, okay, let's just square it because it's easier. It's this term here, right? Now, again, we can expand this into, Wj plus Bj squared. So this is something that you'll see very many times in convergence proofs. You try to look at the change in the tightness or in any of those statements relative to your previous iteration step. Right? So we want to relate this to what we had there plus some change. Okay, so we have this, it's just second binomial formula, plus 2yi xi dot 1 wj plus dot b and bj. Right? So this is our linear function, remember? That's this thing here. We know we made a mistake, so this actually has to be less than 0. And then we get just the norm of xi and 1 squared. Okay. Now, so by exploiting the fact that we made a mistake and that this is bounded, we get that this is simply this term here plus r squared plus 1. Now, after I've made j mistakes, I can bound this, therefore upper bound it, by j times r squared plus 1. Okay? So now all I do is I plug this quantity in up here. And now something interesting happens. The left-hand side, by step 1, as we saw, grows linearly. The upper bound only grows with a square root, right? And so therefore, we must have, so it grows much more slowly. So therefore, there has to be one point where that inequality cannot go any further. And this is where the update and the algorithm has to stop. Basically, after that, I cannot be making any more updates. And okay, so we have j times rho is less equal than 1 plus this term here, which is upper bounded. And so then, if you just solve for j, you get the theorem. So it's a very, very simple update, very simple convergence proof. Okay. Any questions about the proof?
How do you know that, I mean, when you are solving for j, you are assuming equality. How do you assume that equality actually is attainable?
Well, okay, very good question. Can I ever attain an equality? No, I don't have to assume that. I could actually get lucky and find a large margin separator that separates all the data a lot earlier. So all we get from this is a worst case bound, which says, well, you are guaranteed not having to spend more than that many steps until you will have found a separator. But you might very well get very lucky, and already after one step you're done, and you will not make any more mistakes. So all it is we just have a linearly increasing term. We have a term that increases with square root of the iterations. And so therefore, at the point when both meet, okay, let's draw it in pictures. So we have a linear term, we have something that goes like square root with a different constant up front. This is the point where you cannot iterate any further. You could be done already by here, but the amazing thing is that this bound holds regardless of how I order the observations. So this is an adversarial guarantee, because an adversary could be quite evil and reorder all the things in such a way that, for instance, in a class, the first 80% of the class are really boring and easy and everybody falls asleep, and then in the last 20% I pack in all the hard stuff, and you'll still be able to catch it, right? Of course, it would be more interesting if all the interesting things happened in the first 20%, and then you can go home and get on with your research. But basically, this is the nice fact about an adversarial guarantee. A lot of convergence analysis is expressed in that form. There's a lot of really nice links to computational game theory. So if you're doing game theory, you should look this up. This is way beyond 10.7.15, but if you're interested in that, talk to me later and I can point you to some papers, and also, yeah, basically talk to your advisor. Okay. So one of the nice consequences of all of this is you only need to store the errors, because everything else you already knew anyway. This also gives you a compression bound for the perceptron, right? Because it basically means that if you have a very easy problem, you only need to store a very small number of prototypes in order to know how to linearly separate everything. And the other nice thing is that it actually is stochastic gradient descent with regard to the hinge loss. And yeah, basically, this only works if you can properly linearly separate things. Any questions so far?
For that bound, you need like the condition number of the prong, right?
Correct.
You assume you know it a priori, but you know these wrong. Because otherwise, you don't know how hard it could be, right?
Okay. Actually, let me pose that question to the rest of the class. Do I need to know, in order to run this algorithm, how hard the problem is? Basically, do I need to know rho before I run the algorithm?
Not to run the algorithm, but to know like that you just need a finite or like a very small set of examples and not like a big one. No,
Okay.
you can run it without knowing rho. But if you have a huge data set and you're like, oh no, I just need 10, then you need raw for that.
Yes. Yes. Okay, so you've pretty much answered that question yourself, right? It's a very nice observation. Namely, first of all, in order to run the algorithm, I don't really need to know rho. So that's very nice, because basically I get an algorithm that essentially is as nice as it can be without really knowing the hardness of the problem. That said, if I wanted to be able to say, okay, after having seen those 10 observations, I'm done, I would need to know the difficulty of the problem beforehand. That said, even in this case, I wouldn't necessarily have a guarantee that I've really solved the problem properly, right? Because let's say my bound tells me you're not going to make more than 100 mistakes. I run the algorithm, and I'm almost entirely through the data set, and I've only made 20 mistakes because I got lucky. So this was your question from before. So then, am I going to make another 80 mistakes between now and the end of the data set? Nobody knows, because actually an adversary could have reordered the data in such a way that this is not going to happen, or that this might happen. Now, in order to make a statement about what's going to happen in the rest of the data set, I will need slightly different analysis, right? So for that type of analysis, I would basically have to look at how many mistakes have I made in the past since I last updated. And then what is the probability, if the data were not ordered adversarially, but IID at random, that all the bad things could happen in the end. And then you can basically use something like a Chernoff bound or a Chebyshev inequality to figure out what the chances are that you will see something really bad in the end, right? So this requires a very different type of analysis. It's not an worst-case adversarial analysis anymore, but something that is basically a uniform convergence bound, right? So if you do that, you can analyze whether you basically can't just, stop and go home after seeing half the data because you haven't made a mistake on the previous 30-40% of the data, right? In practice, you're very unlikely to get that lucky. But it's quite useful in practice to know what the expected error would be looking forward. Any other questions so far? Okay, good. So we're not going to derive this in detail. You should probably do that by yourself. Instead, we'll look at stochastic gradient descent in a slightly more detail. But basically, the hinge loss is something of a rather nice modification for some of those problems. So this is what I referred to before in terms of, is the problem hard or easy? This is essentially the same data set. As a matter of fact, it is the same data set because I just took the same picture of points and I squished and I stretched it, right? So what I did is I took this set of points that are nicely circular and I squished it in the x-axis and pulled it in the y-axis. So it's the same problem, the same data set really, just that I did some rescaling on the coordinates. You can easily see that this is an easy problem to solve, whereas this has a very narrow margin of separation. So therefore, data rescaling can actually change the convergence properties of the algorithms drastically. With all of that, let's look a little bit at what happens in practice. So here are those data points. And let's say this is my first classifier, color-coded in terms of, redness or blueness. And, well, it gets a few things wrong. And then, okay, if you squint, you would see that, okay, so this observation, so it changed. And it'll see another observation, and it changed. And you can probably look at that much better on the slides later on your own laptop, because the color rendition isn't very good. But what you can see is that initially the hyperplane flips around a lot. Later on, the changes become much smaller. Question, why is that the case? Why will the hyperplane typically change a lot less dramatically as we run the algorithm.
Because the norm of W times, the norm of WBI increases linearly, so you just add a little bit, so it's like 1 over the
Correct.
iteration.
Perfect. So since our current parameter estimate is already getting larger, so therefore the relative size of the increments is smaller, and so therefore we should see less of a change. Again, this only happens if not an adversary has ordered the data in such a way that all the tiny observations happen in the beginning and the monstrously huge ones in the end. But if we can assume that the data is not pathological, all is good. Okay, good. So then let's move on to something a little bit more general, stochastic gradient descent. So the first thing that I should probably do is look a little bit at objectives that we could actually play with. And what we'll see is that the Perceptron algorithm is just an example of that. Okay, how much time do we have left?
-9.
Minus 9 minutes. Oh, okay, well then we should probably stop here, because otherwise somebody will get upset. Okay, so then I'll see you on Wednesday.